Harmonic distortion is a deviation from the ideal sinusoidal waveform of an electrical signal. It occurs when nonlinear loads, such as computers, uninterruptible power supplies, and other electronic devices, draw current in a distorted manner. This distortion can introduce harmonics which are multiples of the fundamental frequency. Excessive harmonics can have detrimental effects on electrical systems. Firstly, overheating. Harmonics can increase the heating of transformers, cables, and other electrical equipment. This can accelerate insulation aging and damage the equipment. Secondly, neutral current overloading. Nonlinear loads often create an unbalanced three-phase system, which results in high neutral currents. Excessive neutral currents can overload the neutral conductor and cause overheating. Thirdly, resonance. Harmonics can resonate with the electrical system's natural frequencies, resulting in voltage spikes and equipment damage. To mitigate the effects of harmonics, several strategies can be employed. One strategy is to install harmonic filters. Harmonic filters are devices that remove harmonics from the electrical system. They can be passive, tuned to specific harmonic frequencies, or active, continuously adjusting to filter a broad range of harmonics. Another strategy is to improve grounding. Proper grounding provides a low impedance path for harmonics to return to the source, reducing their impact on the system. Another is to use shielded cables. Shielded cables help reduce electromagnetic interference and harmonic propagation. You can also limit nonlinear loads. If possible, reduce the number of nonlinear loads connected to the system. Another possible solution is to consider harmonic-tolerant transformers. Transformers designed to tolerate harmonics can handle higher levels of harmonic distortion without overheating. Regarding a specific situation where a 225 kVA 460/230 volts transformer is overheating, it is likely due to harmonic distortion. The following steps are recommended. Firstly, measure harmonic distortion. Use a power analyzer to measure the harmonic content of the electrical system. This will identify the severity of the problem. Secondly, install harmonic filters. If harmonic distortion is excessive, install appropriate harmonic filters to reduce it. Thirdly, monitor the transformer. After installing harmonic filters, continue to monitor the transformer's temperature. If the overheating persists, further investigation may be necessary. Fourthly, consult with an electrical engineer. If the overheating issue cannot be resolved through the above steps, consult with an electrical engineer for further analysis and recommendations. Harmonic distortion arises from the proliferation of nonlinear loads in modern electrical systems. These loads, which include devices like computers, variable frequency drives, and electronic lighting ballasts, draw current in a non-sinusoidal manner, injecting harmonic currents into the power system. These harmonic currents, which are integer multiples of the fundamental frequency, can cause a variety of problems, including equipment overheating, voltage distortion, and increased energy losses. One of the most significant consequences of harmonic distortion is the overheating of electrical equipment, particularly transformers and conductors. Harmonic currents increase the root mean square current flowing through these components, leading to increased I2R losses. These losses manifest as heat, which can degrade insulation, shorten equipment lifespan, and even lead to catastrophic failures. Transformers are especially vulnerable to harmonic-related overheating. The core of a transformer is designed to operate efficiently at the fundamental frequency. However, when harmonic currents are present, they induce additional eddy current and hysteresis losses in the core, further contributing to heat generation. The increased heat can cause the transformer's insulation to break down, leading to winding shorts and ultimately transformer failure. Conductors are also susceptible to overheating due to harmonic currents. The skin effect, which causes alternating current to flow primarily near the surface of a conductor, becomes more pronounced at higher frequencies. This effect reduces the effective cross-sectional area of the conductor, increasing its resistance and leading to greater I2R losses. In addition to overheating, harmonic distortion can also cause voltage distortion. Harmonic currents flowing through the impedance of the power system create harmonic voltages, which distort the sinusoidal waveform. Voltage distortion can negatively impact the performance of sensitive electronic equipment, causing malfunctions, data errors, and even permanent damage. Furthermore, harmonic distortion can lead to increased energy losses in the power system. Harmonic currents increase the overall current flowing through the system, leading to higher I2R losses in conductors, transformers, and other equipment. These losses can significantly increase energy consumption and operating costs. To mitigate the effects of harmonic distortion, a variety of techniques can be employed. One common approach is to install harmonic filters. Harmonic filters are designed to selectively absorb harmonic currents, preventing them from propagating throughout the power system. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of inductors, capacitors, and resistors tuned to specific harmonic frequencies. They provide a low impedance path for harmonic currents, diverting them away from the rest of the system. Active filters, on the other hand, use power electronic converters to inject harmonic currents that are equal in magnitude but opposite in phase to the harmonic currents produced by nonlinear loads. This effectively cancels out the harmonic currents, preventing them from distorting the voltage waveform. Another technique for mitigating harmonic distortion is to use harmonic-tolerant transformers. These transformers are designed with features that reduce their susceptibility to harmonic-related overheating. For example, they may have larger cores, improved cooling systems, and special winding configurations that minimize eddy current losses. Proper grounding is also essential for mitigating harmonic distortion. A well-designed grounding system provides a low impedance path for harmonic currents to return to the source, reducing the voltage distortion caused by these currents. Shielded cables can also help to reduce harmonic propagation. The shielding on these cables prevents electromagnetic interference and reduces the amount of harmonic current that is radiated into the surrounding environment. In addition to these technical solutions, it is also important to limit the amount of nonlinear loads connected to the power system. This can be achieved by using energy-efficient equipment, implementing power factor correction, and segregating nonlinear loads from sensitive equipment. Regularly monitoring the power system for harmonic distortion is also crucial. Power analyzers can be used to measure the harmonic content of the voltage and current waveforms. This information can be used to identify sources of harmonic distortion and to evaluate the effectiveness of mitigation measures. If harmonic distortion is found to be excessive, it is important to consult with an electrical engineer to develop a comprehensive mitigation plan. The engineer can assess the specific characteristics of the power system, identify the sources of harmonic distortion, and recommend appropriate solutions. Implementing a harmonic mitigation strategy can significantly improve the performance and reliability of electrical equipment, reduce energy losses, and prevent costly downtime. The harmonic distortion in electrical systems can lead to a cascade of problems, ultimately affecting the efficiency and longevity of electrical infrastructure. Understanding the root causes and implementing effective mitigation strategies is essential for maintaining a reliable and cost-effective power system. The presence of harmonics can dramatically increase the heat generated within transformers. This is due to a combination of factors including increased eddy current losses and hysteresis losses in the core material. Unlike the fundamental frequency, harmonics induce higher frequency magnetic fields which exacerbate these core losses. The increased heat can degrade the insulating materials within the transformer, leading to premature failure. Harmonic currents also contribute to increased copper losses in the transformer windings. The skin effect, more pronounced at higher frequencies, restricts current flow to the outer layers of the conductors, effectively reducing the cross-sectional area available for conduction. This leads to higher resistance and consequently greater I2R losses. Neutral conductors, particularly in three-phase systems with significant single-phase nonlinear loads, can experience excessive current flow due to harmonic currents. Tripling harmonics, which are odd multiples of the third harmonic, are additive in the neutral conductor, potentially overloading it and causing overheating. Resonance occurs when the inductive and capacitive reactances in the electrical system cancel each other out at a particular harmonic frequency. This can lead to amplified harmonic voltages and currents, which can damage equipment and disrupt system operation. Mitigation strategies must be tailored to the specific characteristics of the electrical system and the types of nonlinear loads present. A thorough harmonic analysis should be performed to identify the dominant harmonic frequencies and their magnitudes. This information is crucial for designing effective harmonic filters. Passive harmonic filters are a common solution for mitigating harmonic distortion. They consist of tuned LC circuits that provide a low impedance path for specific harmonic frequencies. By diverting harmonic currents through the filter, they reduce the amount of harmonic current flowing through the rest of the system. Active harmonic filters offer a more flexible solution compared to passive filters. They use power electronic converters to inject harmonic currents that are equal in magnitude but opposite in phase to the harmonic currents produced by the nonlinear loads. This effectively cancels out the harmonic currents, resulting in a cleaner voltage waveform. In addition to harmonic filters, other mitigation techniques can be employed. These include using harmonic-tolerant transformers, which are designed to withstand the effects of harmonic currents, and implementing power factor correction, which can reduce the amount of harmonic current generated by nonlinear loads. Proper grounding is crucial for mitigating harmonic distortion. A well-designed grounding system provides a low impedance path for harmonic currents to return to the source, minimizing voltage distortion and reducing the risk of equipment damage. Shielded cables can help to reduce the propagation of harmonic currents by containing electromagnetic interference. Regularly monitoring the electrical system for harmonic distortion is essential for identifying potential problems and evaluating the effectiveness of mitigation measures. Power quality analyzers can be used to measure the harmonic content of voltage and current waveforms. Based on the measurements, a comprehensive harmonic mitigation plan should be developed, taking into account the specific characteristics of the electrical system and the types of nonlinear loads present. The plan should include recommendations for selecting and installing harmonic filters, improving grounding, and implementing other mitigation techniques. The effectiveness of the mitigation plan should be evaluated by monitoring the harmonic content of the voltage and current waveforms after the mitigation measures have been implemented. Regular maintenance of the electrical system is also crucial for preventing harmonic distortion. This includes inspecting and testing transformers, conductors, and grounding systems to ensure that they are in good working order. Training personnel on the causes and effects of harmonic distortion can also help to prevent problems. By understanding the risks associated with harmonic distortion, personnel can take steps to minimize its impact on the electrical system. Harmonic distortion is a complex problem that requires a comprehensive approach to mitigate its effects. By implementing the mitigation strategies, electrical systems can operate more efficiently, reliably, and safely. Electrical engineers play a vital role in assessing harmonic distortion and developing effective mitigation plans. Their expertise ensures the integrity and longevity of electrical infrastructure. Understanding the interplay between harmonics and electrical equipment is critical for anyone involved in power systems. From identifying the sources of distortion to implementing tailored mitigation strategies, a proactive approach ensures a stable and reliable power supply. Harmonic analysis is the cornerstone of any effective mitigation strategy. It involves measuring the harmonic content of voltage and current waveforms to identify the dominant harmonic frequencies and their magnitudes. This information is essential for designing appropriate filters and other mitigation devices. Harmonic filters are designed to reduce the amount of harmonic current flowing through the electrical system. Passive filters are tuned to specific harmonic frequencies, while active filters use power electronics to inject cancelling currents. The choice between passive and active filters depends on factors such as the severity of the harmonic distortion, the cost of the filters, and the desired level of performance. Harmonic-tolerant transformers are designed to withstand the effects of harmonic currents. They typically have larger cores, improved cooling systems, and special winding configurations that minimize eddy current losses. Power factor correction can also help to reduce harmonic distortion. By improving the power factor of nonlinear loads, the amount of harmonic current they generate can be reduced. A well-designed grounding system is essential for mitigating harmonic distortion. It provides a low-impedance path for harmonic currents to return to the source, minimizing voltage distortion and reducing the risk of equipment damage. Shielded cables can help to reduce the propagation of harmonic currents by containing electromagnetic interference. Regularly monitoring the electrical system for harmonic distortion is essential for identifying potential problems and evaluating the effectiveness of mitigation measures. The electrical engineer can assess the specific characteristics of the power system, identify the sources of harmonic distortion, and recommend appropriate solutions. Implementing a harmonic mitigation strategy can significantly improve the performance and reliability of electrical equipment, reduce energy losses, and prevent costly downtime.